Hey, pre-calc students, this is Mr. Beck. Today we're going to be talking about our first full discussion in trigonometry. Trigonometry works off of angles and it uses triangles to show the ratio of the sides based off of the angle that we have. That's a lot to say, and to really understand what it means, let's kind of delve into it. So I have a triangle here. I have a certain triangle. Here's my angle, theta. Now, opposite that angle, theta, I have a side that I'm going to call opposite for that reason. Adjacent to the angle, I have adjacent, and then we have the hypotenuse, assuming this is a right triangle. So for any three sides of a triangle, we can write the ratio of two of those sides in 6 different ways. So I have opposite over hypotenuse. I can do its reciprocal, hypotenuse over opposite, adjacent over hypotenuse, hypotenuse over adjacent, opposite over adjacent, and adjacent over opposite. There are only 6 different ways that we can write the ratio of two of these sides. Now, each one of these ratios, we give a certain name. And from geometry, a lot of you will remember that we have what's called SOHCAHTOA. SOHCAHTOA. So with that SOHCAHTOA, it was a very helpful way of remembering that the sine ratio is what we call the opposite over the hypotenuse. So that specific ratio of opposite to hypotenuse is what we call sine. We have cosine, which is the adjacent over hypotenuse. And then we have tangent, which is opposite over adjacent. Those are the 3 that you should remember. Now, the 3 that we didn't talk about in geometry are going to be the 3 reciprocals. So we have cosecant, which is the reciprocal of sine, and that is the hypotenuse over opposite. We have secant, which is the reciprocal of cosine. And then we have cotangent, which is the reciprocal of tangent. So those other 3 ratios that we're going to end up talking about starting this unit are going to be the 3, a lot of times we call them the cofunctions, although the cosine is really the true cofunction. Anyway, these are the 3 other ones, cosecant, secant, and cotangent. So we're going to begin, and the approach that we're going to take when it comes to trigonometry, we're going to focus on what's called a unit circle approach. That unit circle approach relies on us using the unit circle, meaning the radius of that unit circle is 1. And I'm trying to get rid of my screen. Okay, so the radius of my unit circle is 1. So if you remember, back in the first semester, we talked about x squared plus y squared equals r squared. So if x squared plus y squared equals 1, then we have the unit circle. So from this theta, if we take a look at the sine of theta, remember, is opposite over hypotenuse. So y over 1 is just y. This is special because that means that the y-coordinate on the unit circle is the sine of the theta. So the sine ratio of that triangle that you see there is the y-coordinate. That's what's so special. Cosine of theta is adjacent over hypotenuse. And so if you take a look at x over 1, that means that the x-coordinate on the unit circle is going to be the cosine of that theta. Very special relationship. We're going to delve into that. Tangent of theta is going to be opposite over adjacent, so y over x. Now, I like to tie that into slope. So the slope of this radius is going to be my tangent of theta. So that's going to be a very, very special thing. Cosecant of theta is going to be the reciprocal sine, so 1 over y. That's there. Secant of theta, remember it's the reciprocal of cosine, so 1 over x. And cotangent of theta is reciprocal of tangent, so x over y. And so I will look at problems 1a and 1b. We have 2 points that are on the unit circle here. So for problem number 1a, this point is on the unit circle, and we could verify that if we really wanted to by saying x squared plus y squared, and show that that actually is equivalent to r squared. And then from there, since we know this is on the unit circle, we know that the sine is the y-coordinate. Boom. Cosine is the x-coordinate right there. And then tangent is y over x. So that y value over that x value, we multiply by the common denominator that we have there, which is 3 over 3. Then we get negative square root of 5 over 2. Now the other 3, we could look at it one of 2 ways. We could just reciprocate the sine, the cosine, and the tangent. Or you could look at it as 1 over x, 1 over y, 1 over x, and x over y. Both ways are very, very appropriate for us to look at. So a lot of times we will just reciprocate the 3 values that we have there. So the reciprocal of negative square root of 5 over 3 is 3 over negative square root of 5. And of course, we must rationalize that. Reciprocal of 3 halves. So the reciprocal of 3 halves is our secant, which is, reciprocal of 2/3, which is 3 halves. And that is our secant value. The reciprocal of negative square root of 5 over 2 is 2 over negative square root of 5, which, when we rationalize, is our cotangent value. This one, same thing. We know that we're on the unit circle. We could verify 4/25 plus 21/25 does equal 1. Therefore, it's on the unit circle. Sine is our y. Cosine is our x. Tangent is y over x. Now, what you should notice is because these have the same denominator, they're going to end up canceling each other out, which is what I showed there. Something that's also important, what happens when you have a negative over a negative? It ends up being a positive value. So then we have our 3 reciprocals. So the reciprocal of our y is 5 over negative square root of 21, which ends up being negative 5 square root of 21 over 21. Reciprocate negative 2/5 for our secant value. Reciprocate our tangent and then rationalize to get our cotangent. Now, what happens if our point's not on the unit circle? Which tends to happen more often. The unit circle is going to be our approach if we're going to look at everything, but not every on the unit circle. So if we redraw our triangle, this time we have x squared plus y squared equals r squared. So we have a definitive radius. Sine is still opposite over hypotenuse. So sine is y over r in this case. Cosine, therefore, adjacent over hypotenuse is x over r. Tangent is opposite over adjacent. So the tangent value is really the slope. And if you think about that, the slope is really not dependent on the length of the radius. So it makes sense that the tangent is still going to be y over x. But the sine and the cosine values are now going to be changed because the sine has to be the ratio of the opposite over the hypotenuse. So it's that y over r and that x over r. Cosecant and secant, therefore, are r over y or r over x, respectively. And cotangent is still x over y. So looking back at problem A, the very first thing we need to do is find our radius. So x squared plus y squared equals r squared. R squared ends up being 20, so the radius is 2 square root of 5, and our radius is always going to be a positive value here. So sine is y over r, so 2 over 2 square root of 5, reduced and rationalized. Cosine is x over r, so negative 4 over 2 square root of 5, reduced and rationalized. Tangent is y over x, so negative 2 over negative 4, which is negative 1/2. Cosecant, we could reciprocate each of those individual values, or we could look at cosecant is going to be r over y. And if this is r over y, just to kind of show that, that is 2 square root of 5 over 2, which does reduce 2 square root of 5. Remember, secant is now r over x, and cotangent is still x over y. And we can find those values just by reducing. For part B, we have another point, 4 comma 2 square root of 2. One of the things that I like to do that I didn't really show on any of the other three so far, but one of the things I like to do is say, hey, what quadrant is this in? Let's focus on the circle in that quadrant. So we have the coordinate 4 comma 2 square root of 2. So if we assume 4 is right about there, so we're looking at right about here. So this is 4 comma 2 square root of 2. So the x value is 4, the y value is 2 square root of 2. And what does the radius end up being? 2 square root of 6. You can see the work that I have here for that. X squared plus y squared equals r squared. So then this at least gives me some perspective on where I'm at and what I'm doing. If you really want to, we could work with similar triangles, which is really the whole basis of trigonometry. And I know I haven't gotten into that just yet, but we could reduce these so that they're on the unit circle if we want to. And we could do that by dividing by the radius. Now, I'm not sure if you really want to do that or not, but we can. I know this looks kind of nasty at the moment, but now we can treat it as if it's on the unit circle to have our x and our y and our r. So, that's something fun that you could do, but most students will not like to do that right from the beginning. So let's go back to sine is y over r, reduce and rationalize. Cosine is x over r, reduce and rationalize. Tangent is y over x, so y over x, reduce and rationalize. Cosecant is the reciprocal of this one, so that would be 3 over the square root of 3, which rationalizes just the square root of 3. Secant is going to be r over x. So our r value is 3 square root of 6. I really feel like that should be 2 square root of 6. So secant should be 2 square root of 6. So it's r. Both of these should have been 2. Man, my apologies. I'm glad I caught it. So secant is r over x n. Okay, so secant is r over x. So 2 square root of 6 over 4, which reduces 2 square root of 6 over 2. So that one's actually correct. And then cotangent is going to be the reciprocal of tangent, which is x over y, or just the square root of 2. Actually, let's kind of verify that one just to make sure. 4 over 2 square root of 2, which is 4 square root of 2 over 4, which is the square root of 2. So yes, that one's right. All right, then we have what's called quadrantal angles. And so with quadrantal angles are going to be multiples of pi over 2 because they are on the x or the y axis. So these are going to be multiples of pi over 2, and that's in radians, 90 degrees if you want to stick with degrees. So if we list them out, I do like to list the coordinates on the unit circle. And the reason why I want to use the unit circle is because, once again, we have our values of cosine theta comma sine theta. And don't forget, the slope is the tangent. So what's going to happen here is, if we want to look at 0 degrees, the sine of 0 is going to be our y value, which is 0. The cosine of 0 is our x value, which is 1. Tangent is y over x, or the slope, which is 0. So the slope here is 0. And then we have our 3 reciprocals. So the reciprocal 0 is our the reciprocal sine. The reciprocal 0 is undefined. Reciprocal of cosine is secant. And then the reciprocal of 1 is 1. The reciprocal of tangent is cotangent. And the reciprocal of 0 is once again undefined. And that all corresponds to that point right here. If I do pi over 2, and I really could do this with all of them, I'm just going to stick with 0 and pi over 2 just because working with quadrant 1 tends to be very, very valuable. You'll see why. So we have this coordinate 0, 1 right here. So the sine is the y value, which is 1. The cosine is the x value, which is 0. Tangent, the slope of this vertical line is undefined. Now, if you look at 1 over 0, that's why it's undefined, so 1 over 0. Cosecant, we now have our reciprocals, reciprocal of 1, reciprocal of 0, and then the reciprocal of undefined is 0, which if you reciprocate this, you get 0 over 1, which is 0. We can continue on if we wanted to, cosecant of pi, or sine of pi, cosine of pi, tangent of pi, et cetera, et cetera, et cetera, et cetera. We'd just be then working with the coordinate -1, 0. And that highlights the approach that we're going to take here. The very first thing that I want you to do when you're looking at these kind of problems, when you're trying to work with quadrantal angles, is let's identify what coordinate we are at. If we can identify what coordinate we're at, then we can determine, do we want the x value, the y value, or any of the others. So for part A, sine of pi, pi is going to be this direction at the coordinate -1, 0, and the sine is the y value, as you can see highlighted right there. 3 pi over 2, so 3 pi over 2. If you go 1 pi over 2, 2 pi over 2, 3 pi over 2, now that's associated with the coordinate 0, -1. So cosine is the x value, which is y 1, 0. 5 pi over 2, let's kind of look at this as pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, means we're associated with the point 0, 1. And therefore sine is the y value, which is 1. Cosine of -3 pi over 2, so -3 pi over 2. If I go negative, that would be -1 pi over, let's try it again, -1 pi over 2, -2 pi over 2, -3 pi over 2. We're associated with 0, 1 again. And cosine is the x value, which is y 1, 0. Sine of -pi over 2, so -pi over 2 goes at the coordinate 0, -1. And sine is the y value, which is -1. -3 pi, so -3 pi would go -1 pi, -2 pi, -3 pi. So we're at the coordinate -1, 0. Cosine is the x value, so our answer is -1. -7 pi over 2. So let's go -1, -2, -3, pi over 2, -4, pi over 2, -5, pi over 2, -6, pi over 2, -7, pi over 2. That means that we're going upwards, which is associated with the coordinate 0, 1. Sine is the y value, which is 1. And unfortunately, there's a typo that both of those should not be sine. So I changed g to cosine, and that means that we're still at the same point. Cosine is our x value, which is 0. 24 pi, let's start thinking a little bit more efficiently. 24 pi, if we go in multiples of 2 pi, so we have 0, 2 pi, 4 pi, 6 pi, 8 pi, etc., etc. Every time we have a multiple of 2 pi, we're heading in the original origin direction. So that goes, 24 pi is a multiple of 2 pi. So we can continue counting around if we want to, or we just know it's associated with the point 1, 0. Cosine is the x value, so we want 1. 27 pi over 2. We can count by pi over 2s and go around the circle over and over and over again. Or we could say 2 goes into 27, 13 and a half times. So we have 13 and a half rotations. So if the even, or it's like 2 pi, 4 pi, and 6 pi are all the way at the origin, all of the odd ones, so 1 pi, 3 pi, 5 pi, and 7 pi are going to be over here. We could use that to our advantage to say 13 pi is going to be in that direction, and we have to go an additional half pi, which is why it opens down. And we want the sine value, which is the y value of -1. There are multiple ways that we could look at it, but that tends to be a very, very efficient way of doing this. So we move on, and we move on to developing the full unit circle. Now you can see the full unit circle developed here, color-coded. In black, or I guess dark gray, what I have there are the quadrantal angles listed. Now here I have all of the angles, I have all of their radian measures, and then I have the coordinate associated with it. Now, to develop these coordinates, what we did was we took a look at a square. A square has 90-degree angles, where if we draw a diagonal, it forms a 45-degree angle. And then we could find the sine and the cosine value of all of our 45-degree angles by saying sine is opposite over hypotenuse. So the sine of 45 degrees is 1 over the square root of 2, rationalizes the square root of 2 over 2. And that's where I got that y value right there. The cosine is going to be the adjacent side over the square root of 2 over hypotenuse, which ends up also being the square root of 2 over 2. Now, what I did with that was, if you take a look at all of these greenish colors, teal colors, so all of our 45 degrees I have marked here. All of the 45 degrees that are not already quadrantal angles I have marked there. And so what we could do is we could use the symmetry of the circle to say, okay, all of these are still 45 degrees if we take a look at them in relationship to the x-axis. They're all 45 degrees, they're going to create the same ratios. Therefore, we're going to use the symmetry to say, okay, the ratios are the same, but what's different are the x and the y values. So here in quadrant 2, the x is negative. Quadrant 3, the x is negative. Quadrant 2, the y is positive, and quadrant 3, the y is negative. So we can use those exact same ratios for all of our 45-degree angles, the 45, the 135, the 225, and the 315. Those are common angles. If you remember on last time's notes, I had those common angles listed. Now, let me remove some of those colors and say, okay, now let's focus on the red. The red are going to be my 60 degrees or my pi over 3 angles. So the way that we can come up with that is take an isosceles triangle and drop an altitude, where if the side of the isosceles triangle is 2, and that forms a right angle, that cuts the 60-degree angle in half to just a 30-degree angle. And it also cuts the side in half, so that leg is 1. If you remember from geometry, we do have a 1, 2 square root of 3 relationship when it comes to a 30, 60, 90 triangle. We're going to use that to our advantage when we start off with the sine of 60 is the opposite over hypotenuse, which is how we get the square root of 3 over 2. And then the cosine of 60, I don't have it listed there, but the cosine of 60 is going to be adjacent over hypotenuse, which would then be 1 over 2. So our x value is 1 over 2, our y value is the square root of 3 over 2. And then we could use the symmetry by adding 60 degrees, and the x is negative and the y is positive. That's all based off of now this, what we sometimes call a reference angle. So here the x is negative and the y is negative. Here the x is positive and the y is supposed to be negative. It doesn't actually have a negative listed there, but now it does. So with our 60-degree angles, our pi over 3s, so pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, they form the coordinates that are 1/2 and square root of 3 over 2. Whether they're positive or negative are based off of which quantity they're in. Then we take a look at our final set of angles. Our final set of angles are going to be our pi over 6s. So half of pi over 3 is pi over 6. So half of 60 is 30 degrees. And we could use then the 30-degree angle that we had in that equilateral triangle that we cut in half. So the sine of 30 is 1 over 2 because it's opposite of our hypotenuse. Cosine of 30 is the square root of 3 over 2. And so therefore, if we do our cosine comma sine, we get that coordinate, square root of 3 over 2, comma 1/2. Excuse me. And we could use that to develop our other coordinates. So 180 minus 30 gives me the 150-degree angle. 180 plus 30 gives me the 210-degree angle. And 360 minus 30 gives me the 330-degree angle. And then if we do that in radians, pi minus pi over 6, pi plus pi over 6, and 2 pi minus pi over 6. And that'll give us all the other coordinates that we see there. So this unit circle is going to be very, very important for you to know and develop. And I say that because if you could draw out and write the unit circle over and over again, you're going to start tying these coordinates together very, very closely. And that's exactly what we need. So if you notice right here, for example 4, what I did was I recreated the unit circle here, and it looks a little bit more appropriate. When it comes to this unit circle, what we have, and what's kind of important here is I want to find the exact ratios of the 6 trig functions, and I did change my directions on that one. So to find 6 trig ratios, first thing that I need to do is identify where is the angle that I'm looking at. So 7 pi over 6 is right here. And then I could find the sine, which is the y coordinate, the cosine, which is the x coordinate. And the tangent is our y over our x. Our y over our x is -1. I know I don't really have that written there, but our y over our x is -1/2 over negative square root of 3 over 2, which if we multiply by 2 over 2, you get -1 over the square root of 3, negative square root of 3. They're both negative, so that's a positive value. And if we multiply by square root of 3 over the square root of 3, we will get what we have listed here as the square root of 3 over 3. And then you can reciprocate those ratios to find the cosecant, the secant, and the cotangent if you wish. Or you could still do this as 1 over x, 1 over y. So our cosecant is 1 over y, our secant is 1 over x, our cotangent is x over y, and you can algebraically do it that way. But you should see the pattern that I'm having here saying, okay, where is the angle? From that angle, in this case, -5 pi over 4. So we have -1 pi over 2 over 4, -2 pi over 4, -3 pi over 4, which is right here. Then -4 pi over 4, -5 pi over 4 takes me to this 3 pi over 4 angle. So it's coterminal with 3 pi over 4. The sine, therefore, is the y value, which is positive. Cosine is the x value, which is negative. And then the tangent is going to be the slope, or y over x, whichever way you want to look at it. But that ends up being the slope of -1. And then reciprocate. And it's going to be pretty useful for you to know that the square root of 2 over 2 reciprocates to the square root of 2, because you're going to be using that a lot. So just like it's going to be important for you to see that the square root of 3 over 3 and the square root of 3 both reciprocate to each other. So with that said, let's continue on. What we're going to do is we're going to associate what coordinate are we at. And you could use the unit circle to help you, but eventually you want to move away from it. So what coordinate do you have? And then which do we want, the x or the y value? So the sine of 5 pi over 3, 5 pi over 3. And let me go ahead and clear off my angles a little bit. So 5 pi over 3 is going to be right here. Sine is the y value, so I want that negative square root of 3 over 2. Negative 210 is coterminal with 150 degrees. So that's associated with the negative square root of 3 over 2, comma 1/2. Cosine is the x value, which is why I wanted that x value of negative square root of 3 over 2. 120 degrees. 120 degrees is right here. Sine is the y value, so positive square root of 3 over 2. 240 is right here. Cosine is the x value, so negative 1/2. That's how I get that. And continue on over and over again. So 315, if you notice I'm moving that out of the way. 315 is the coordinate positive square root of 2 over 2, negative square root of 2 over 2. Once we have that coordinate, cosine is the x value, so that's why it's positive. 210 degrees is the coordinate negative 1/2. Actually, it's negative square root of 3 over 2, comma negative 1/2. And with that in mind, sine is the y value, so it's the negative 1/2. Negative 45 degrees is positive square root of 2 over 2, negative square root of 2 over 2. Sine is the y value, which is why I wanted the negative. And we can continue on with that process. Now, example number 6, what I have here is to find the exact value. It's really just kind of putting a couple of these problems together all at once. So the sine of 60 minus the secant of 60. 60 degrees, if we associate that coordinate with 1/2 comma square root of 3 over 2, we will take our y value here minus the reciprocal of the x value. That's how we get minus 2. So if we write that 2 as 4 over 2, we can put it together as one big fraction, square root of 3 minus 4 over 2. 45 degrees, secant is going to be the reciprocal, as you can see here, of square root of 2 over 2. And that's because that's a 45-degree angle. So square root of 2 plus square root of 3 over 3, which if we have a common denominator, 3 square root of 2 over 3 plus square root of 3 over 3, we could write it as one big fraction. And then put it more and more together. Cosine of pi is over here. That would be the coordinate negative 1, 0, so the cosine is the x value. Cotangent of pi over 4 is going to be right here, and the slope of that is 1, so the reciprocal of the slope, which is what cotangent will give us, is also 1. Sine of negative pi over 2 is down here, associated with the coordinate 0, negative 1, and sine is the y value. So this problem just adds together to get negative 3. So as I mentioned, understanding the reciprocals of these numbers are going to be very, very beneficial. But still, what we're going to be doing here is finding the coordinate and then reciprocating based off of which of the trig functions we want. So you can see here that 225 degrees is associated with the coordinate negative square root of 2 over 2, comma negative square root of 2 over 2. We can see that from the unit circle here. And then secant would be the reciprocal of the x. So the reciprocal of the x, if you use the chart that I have up here, you're welcome to, but the reciprocal is negative square root of 2 over 2. 210 degrees, what you can see here is I drew a line that had the slope of square root of 3 over 3. And that you can still do this as y over x. I know I haven't shown as much here, or at least in the video notes, I focus on that slope, but knowing that slope is very, very beneficial. So that slope, by the way, I'm drawing up here. Slope is square root of 3 over 3, 1, and square root of 3. So if you want to look at slopes that way and reciprocate them respectively. Anyway, cosecant is the reciprocal of our sine value. So again, what's the point? Knowing the point and then reciprocate the y value for the cosecant. Cotangent 150, so I take a look at the slope at 150 degrees. That slope at 150 degrees is negative square root of 3 over 3, and then reciprocate it. 315 degrees, what's our, because it's cotangent, I want the reciprocal of the slope. The reciprocal of negative 1 is negative 1. And you can see here that I'm doing the exact same thing over and over and over again. What's the coordinate? What's the slope? Once we know the coordinate, once we know the slope, we can either take the x value, the y value, the slope, or the reciprocal of any of those values. And that's how I get everything else that's listed here. Now, the last ones are they are terminal angles, or not terminal angles. They are quadrantal angles. There you go. I kind of struggle with that a little bit. So they are quadrantal angles, and those quadrantal angles, again, we still associate what's the coordinate there and then reciprocate. And you can see the last four of those are all undefined because they're all end up being the reciprocal of 0. Now, in the calculator ends up being one of the harder things for us to worry about because we only have sine, cosine, and tangent. So to come up with all of the other ones, then we have to reciprocate the angle. So to find the cosecant of 140 degrees, we have to take the sine of 140 and reciprocate it and throw it in the calculator. So A and B were pretty easy to do because you just throw them in the calculator. For D, we need to know, okay, what's the tangent of 97 degrees and then reciprocate it. Make sure that you know how to use your calculator to do the difference between degrees and radians. So you have a button that typically says either D or G for degrees, radians, and gradients, or you have a button that says deg on it for degree, and you want to turn it into radians when you're working with actual radians. So 1 over the tangent of 2 pi over 9. Secant, this is going to be 1 over the cosine of 3 pi over 5. This is 1 over the sine of negative 6 pi over 11. And the secant would be 1 over the cosine of negative 24. And this, yes, is a radian, and you know it's a radian because there are no degrees right there. So hopefully this was very, very helpful for you. This is Mr. Beck, and I am signing up.